Everyone should be able to actually do this. What I want you to do is to take these equations, and what I want you to do is to come up with an equation that's in this form. That the RPM, remember, the frequency times 60 equals RPM. Okay? What I want you to do is to derive a formula that says RPM equals, and it will be some function. And it will be a function of several parameters like L and G and this little R disk, that little quantity, and the angle and the alpha angle. So it's going to be some function. I'm not going to tell you what that function is. That's part of what the extra credit is. Now let me give you a hint. This is very doable to come up with this function that says RPM equals some function. It's going to take a little bit of work, though. It may not immediately just jump out at you. But you can do it. I know you can. And, oh, notice this. I gave you some hints on page 7. Well, that should make it easy. I even give you some hints. Okay, on to page 8 and part D. In part D, once you do part C, it leads right into part D, and hopefully part D extra credit is self-explanatory, sort of, kind of. What I want you to do is to use this function and to make some plots. And I even give you an example plot of what, actually, when I calculated it, of what one of these plots looks like. Now this is not, the data I give you is different from what's shown at the bottom of page 8. So don't just copy what's on the bottom of page 8, because that's actually for different data. And I'll recognize it if you use it. So, so I was a little bit tricky there. But so what you're going to do is you're going to plug in some numbers into here, and this will be a wonderful exercise to do this in Excel. You can do it by hand, but it's so much quicker in Excel. So anyway, that explains this slab, this rotational motion and centripetal force lab. If there's any question, just call me. What we're going to do now is briefly go over the next numerical lab, and this will probably be rather short because most of this lab is this is the HARC numerical lab number 7. The main reason for this lab, well, there's, I guess, two main reasons. One is that the gravitation is such a big topic that there's some things that the book doesn't cover. In particular, one of the standard things that often is covered in physics classes are Kepler's laws. And so if you look on the first couple of pages, I have actually, let's see, 1, 2, 3. If you read the first 3 pages, you'll get a brief history into Kepler, what he did, and on page 2, it will go over Kepler's 3 laws. And you need to read this, you need to pay attention, and turns out that Isaac Newton, Kepler came first, Isaac Newton came second. Isaac Newton was after Kepler. But Isaac Newton's law of gravity definitely it was built upon a lot of the work, or at least some of the work done by Kepler. And as a matter of fact, Newton was able to verify that one of Kepler's ideas, and one of the things that he was so famous for, is the idea that planets, if this is a sun, whoops, let me switch, that if this is a sun, that the planets orbit in an elliptical fashion. Now it can be circular, oftentimes they are circular, but in general it's an elliptical orbit. Okay, and in particular, his law number 3 on page 2, which you'll see, first law and on page 3, is very important. And it's the idea that that for planets, the ratio of, let's see, the ratio of the square of the period to the cube of the radius is a constant. That is, if you take a planet here that's orbiting the sun, and it has a certain period, a certain amount of time, and then there's a certain r. Let's just assume right now this is a circle, just to keep it easy. That the ratio of the square of the period to the radius cubed is equal to a constant. And this is and so one of the things we're going to do in this lab is to actually, in this numerical lab, is to check this. So if you look on page well, we'll do 1, 2, 3, 4. On page 4, there's problem number 1. And on page 5, there's problem number 2. One of the things I'm going to want you to do, actually, I have this in reverse, the way I have it here, r3 divided by t squared, same constant. Oh, excuse me, it's just the reciprocal. But notice on page 5, in problem 2, I list all the planets, even Pluto. Pluto is now not considered a planet, unfortunately. But and we have the distance, the mean distance from the sun, their orbital period in seconds, and convert this to years. And I want you to see if, in fact, this really is a constant for all of the planets. Okay, now flip back to page 4. Flip back to page 4 to problem number 1. And problem number 1 is this. Suppose you're Isaac Newton, and it's 1672, which means you're about 30 years old, and you have just derived the law of gravity, which is big G, mass of the sun, times the mass of the planet, divided by the radius squared. Okay, you have just derived this, and you actually invented calculus in order to derive this. So you have the invention of calculus nicely tucked under your belt also. And now you decide, you remember back Kepler, who died about 40 years ago. If you're about 30 years old, Kepler would have died about 40 years ago. He died about 10 years prior to Isaac Newton being born. So you think of Kepler's third law, which says that the radius cubed divided by t squared equals a constant. Okay. So you think that based on this, or your new law of gravity that you just discovered, that you will be able to prove Kepler's third law once and for all. Now Kepler, you'll be able to prove it. So what you need to do, either at the bottom of page 4 or on a separate piece of paper, is to, using this gravitational law principle, and assuming an orbit, a planet is orbiting the sun, I want you to prove Kepler's third law. Okay, and I'm sure Isaac Newton did this. In fact, he did. So you can do it too. Okay, that's page 1. That's problem 1. problem 2 on page 5, and then problem 3 on the page 6. I want you to write down write down Kepler's 3 laws. I want you to write them down. You can write them in your own words. That's fine. And then problem 4 on the bottom page 6. Before you answer problem 4, I want you to read the rest of the pages here. Is the introduction to black holes. Everybody's very interested in black holes, and I think you'll find it very fascinating. It's very easy to read, and it only takes about three and a half pages. And then back on page 6, problem 4, there's a problem I want you to do, and it's a very easy calculation, but in a black hole, okay, basically, if you look at the evolution of stars, how stars are, according to what astronomers say, stars are kind of the life and death cycle of a star. A star goes through different phases, and one of a star toward the end of its life, if you will, can go into what's called a black hole. Essentially, a star, let's say I'm just going to go over this real briefly. What happens is there's 2 major forces that operate. This is a star, say the sun. There's 2 major forces that are operating inside the star. There's, of course, this is all star material. There's gravity, which is pulling this material into the center, just like gravity pulls all the Earth, keeps the Earth together. Okay, but there's also a nuclear force, the fission that's going on. It's the nuclear fusion that's going, fusion that's going inside the sun, that's pushing it out. Okay, and so there's a very healthy dynamic going on here, obviously, and so the star, the size of the the star doesn't collapse because there's this nuclear fusion going on that's pushing, essentially pushing material out, but there's also gravitational that's pulling it back in. Okay, and so you have this dynamic balance going on. Now, as a star ages, what happens? It has burnt up a lot of its fuel, and so it's burnt up some of its fuel, and what happens is an imbalance occurs. An imbalance can occur, and the star, there's more, the gravitational, the burns of some of this fuel, the gravitational force isn't as much because it's lost some of its actual material. Gravity doesn't hold it quite as much, and the star actually starts to grow. Okay, it can grow. The nuclear pressure pushes out more and more, and the star actually starts to grow, and it can grow sometimes into what's called a red giant. Maybe you've heard of this, grow into a red giant, where it's, and it's the spectrum kind of shifts more to the red region. That's why it's called the red giant. The temperature cools down a little bit. It's not quite as hot because now it's expanded some. So it shifts more to the lower frequency, or the red region. The size gets larger. Now what can happen then is you can actually, this can actually waffle back and forth, but at some point it gets out so big that the nuclear reaction doesn't quite sustain itself. And then if you start losing the nuclear reaction, this all material will collapse back on itself. And so suddenly you get this catastrophic event where this stuff, the star material, actually starts collapsing back down. Okay, it collapses back down, and it shrinks to real size, and this happens very quickly, of course. Shrinks size, and it shrinks down, and it gets to this point, and then all the material kind of collects in here, and it reheats, and suddenly it can explode. The nuclear fission process kind of quickly fires up again, and it just explodes out. Okay, and we call that a nova. Or sometimes, if it's a real big one, called a supernova, a nova. That's where the star, it expands, but it collapses back down. It comes to a central, kind of a condensed area where it reheats and it explodes. Okay? Now, after it explodes, and depending on exactly the nature of this, it's also possible that it doesn't explode. It's also possible, well, that the couple things could happen. It could, if it some of them, when some you can have a nova happening where some of this material then explodes out, but not all of it. And what's left is what's called a dwarf. A dwarf star, maybe you've heard of that. It's kind of the remnants it's the core material of what was inside this nova. Okay. Now this tends to be pretty much what astronomers called like a dead star. A lot of the nuclear material has been spent. There's still material there, but it's what the explosion has scattered a lot of the nuclear material out. Now, if you look at this dwarf star, if the mass of this, if things are massive enough, then this, when this material comes back together again after a red giant, if this dwarf has enough mass, it can turn into what's called a black hole. And that's only if it's massive enough. If it's massive, and what happens is this core material, there's enough mass in here to where the gravitational attraction is very, very large, and it's so large that the gravitational attraction just pulls everything in. It pulls everything in, and it pulls the mass is so large and gravity is so strong that it pulls it in. Actually, mathematically, it pulls it into an infinitesimal point. That's what we call a black hole. Okay, and the laws of physics, physicists say, tend to break down at that point. You can still do some physics with it, and people, some of you've heard of the great a British physicist called Stephen Hawking. Became very famous for a lot of the papers he did regarding black holes. Okay. So now what makes a black hole black? What makes a black hole black is that gravity, here you have a black hole, let's say, and actually when we draw a black hole, really what we're drawing is what we call the event horizon. Okay? Once you it's a boundary. Once you cross that boundary, there's no going back. You are sucked in, and conceivably you die, although nobody has ever done it and talked about it, so no one really knows for sure. The physics gets awfully messy inside here, and so honestly, no one really knows exactly what happens inside a black hole, but it's probably not pleasant. You'll probably be immediately crushed because of the intense gravity. But the gravity is so large that not even light can escape. Okay, so so light, even if it tried to escape, basically you might think it just circles back around. Its gravity is so intense that a beam of light cannot even escape. That's why we give the name a black hole. Okay, and here's a formula for what I want you to do is you take the mass of the sun and to find out what the radius of this black hole would need to be in order for the black hole, in order for the mass of the sun to become a black hole. So in other words, we're going to take all the mass of the sun, shrink it into a real small radius. At that small radius, it would turn into a black hole. And this is an approximate formula of how to calculate that. It's R equals 2gm divided by c squared, where this is c is the speed of light. Speed of light is 3 times 10 to the 8th meters per second. Okay. All right. Well, we hope you like this introduction to the black hole. If you have any questions, we can love to talk more about it. Also, I forgot. The very last page, I have 2 extra credit problems. The first extra credit problem, again, is self-explanatory. It's talking about the space shuttle, and there's some data on the space shuttle, and all you need to do is just work out some physics with how the space shuttle orbits the Earth. Okay. The next page, the very last page, or the last 2 pages, is for those of you who are really interested in orbital physics, which is a fascinating subject in and of itself. The idea is that here you have the Earth and you have a satellite, but you can have a satellite that goes like this, okay, where this is an elliptical orbit. Say this is the Earth, elliptical orbit, okay. You can have a satellite that actually makes this kind of pass around the Earth. It doesn't have to be centered directly around the Earth. Remember, Kepler's law says that something that orbits a planet or the sun is an elliptical orbit. So there's 2, you remember how you draw an ellipse, you have 2 foci, they call it. And in this case, you have the Earth is a center of one of the focal points, the foci, and the other one is out here in space. Okay? So, and what I do is I give you the equation in polar coordinates. Now, hopefully you all know what polar coordinates are. I'm going to replace this. Suppose what we do is we put an x-axis, an x and a y-axis, say right at the Earth, and we look at r and theta. And basically, we're saying r is some function of theta. Okay, and as we sweep theta around, our r changes. Okay, as theta sweeps around, our r changes. So, in this case, the formula is okay, where the shortest distance here is called RO, that's the shortest distance at theta equals 0. By the way, theta has to be in radians. Theta has to be in, well, Actually, the way it is, it can be in degrees or radians, but typically we think of it in radians. Okay. But we could also, because we have the cosine of the angle, we could also use this in degrees. Okay. And E is called the eccentricity. And we're not going to go over this now, but you can read about it. If you're interested in doing this, this problem, there's a Halley's Comet example on page 2 of this extra credit problem. Please, I'd love for you to try this, and if you have any questions, please just call me or send me an email. Well, that about wraps it up for now, and we'll talk with you later.